Dirac bug model in strong magnetic fields. Okay.
So
Please.
thank you for the introduction, and I would like also to thank the organizers for this nice conference. So if you have questions, do not hesitate to interrupt me, because I will not see in the chat if someone is asking a question. So this talk is actually a Blackboard talk, as you can see. And so I am going to talk. I'm going to talk about the Dirac bug model in strong magnetic fields. And I have to say that it is a joint work with Jean-Marie Barbarou, Loïc Letrust, and Edgardo Stockmeyer. And the corresponding paper is on the archive, and here is the number of the preprint. So first, I have to explain what the framework of this talk is. So this is my first part, the framework. So the framework. So in this talk, I will be in two dimensions, and so let me draw some omega, some domain omega in R2. Omega is supposed to be bounded, open, of course, smooth enough. So I will not consider such a question of smoothness. So C infinity, if you want, smooth enough, and simply connected. Connected, simply connected. Like that. And I will also consider the outward pointing normal. So something like that. N. So I will use this convention for the orientation of the normal to the boundary. So this talk is about magnetic fields. So I have to introduce the magnetic field. So B will be the magnetic field. So a smooth function on omega. So valued in R. So the magnetic field. The magnetic field, and corresponding to this magnetic field, we use vector potential A. So vector potential, as we already saw in a few talks, vector potential. And B equals D1 A2 minus D2 A1. So, and the vector potential is assumed to be also a smooth function on omega. So like that. So this is the magnetic field, the vector potential. And so what is the operator? So this talk is devoted to the following operator: the magnetic Dirac operator. So magnetic Dirac operator. So this is a differential operator, the following differential operator, D. So HA. So H will be the semi-classical parameter. A is the vector potential. So it takes the form sigma dot P minus A. So I will tell you what sigma and P are in a few minutes. So this operator is a matrix here, 0 on the diagonal, and some operator here, DHA, and its formal adjoint, DHA star, like that. So where? So what are these things? So DHA is minus 2IH dz. So dz is the usual Cauchy-Riemann derivative, minus A1 plus IA2, and DHA star is essentially the same, but with the anti-Cauchy-Riemann derivative, minus A1 minus IA2. And so what are these sigmas? So we already saw this sigma in the talk by Michael Persson-Sundquist. So here comes sigma. So sigma is sigma 1, sigma 2. Sigma 1, sigma 2. So the famous Pauli matrices. So I recall that sigma 1 is 0, 0, 1, 1, like that. And sigma 2 minus I, 0, 0. And probably I will need also the third Pauli matrix, sigma 3, which is 1, minus 1, 0, 0. And I also use the notation for P. P here is the usual derivative, gradient operator, minus IH gradient. And of course, H is a positive parameter, so the semi-classical parameter. Okay, so here you have the action of the operator, so this magnetic Dirac operator. And to get an operator, you need to specify a domain, and to get this domain, I need to describe the boundary condition. So that we are considering here. So boundary condition. So the boundary condition is the so-called MIT bag boundary condition. So it is related to the following operator, B, like that. So this B is not the same B as you have here. Okay, it's B for boundary here. So B is an operator on the boundary. So
excuse me, Nicolas, just
yes.
Yes, Nicolas, just to be sure, in your matrix notation for DHA, on the right-hand side, where is sigma? I don't understand.
Sigma is hidden in the D. Yes, sorry. So yes, I understand your question. So here it's sigma 1, P1 minus A1 plus sigma 2, P2 minus A2, like that.
Okay.
And so if you replace P by its expression and sigma 1 by its value, you can write the operator in this form. Is it clear?
Right.
And
yes, it's clear.
It's clear.
Thank you.
And so this boundary operator B is valued in the 2x2 matrices, like that. And B in this talk is minus I sigma 3, so the third Pauli matrix, times sigma dot n, like that. And I also use the same convention I just explained here, that sigma dot n, where n is the outward pointing normal, it's n1 sigma 1 plus n2 sigma 2. So here is the boundary operator, and the boundary condition is the following. So the domain of the operator, if you prefer, the domain of this operator DHA is a subset of H1. So phi in H1 of omega, valued in C2. So you have phi is a spinor, and such that B phi equals phi. And if you compute explicitly sigma 3 dot sigma dot n, you can rewrite this condition just as phi 2 equal to I n phi 1. So where n is n1 plus I n2. N1 and N2 being the two components of the outward pointing normal. So what can we say about this operator? First, this operator, DHA, with this domain is a self-adjoint operator. So this operator is self-adjoint. And this has been proved, for instance, in a paper by Ben-Gurion, in a paper by Ben-Gurion, Fournet, Stockmeyer, and Van den Bosch. In 2017. So, for instance, this operator has also compact resolvent. It has compact resolvent. And so we can describe its spectrum like that. So you have this operator, so is not bounded from below or from above, and so you will have positive and negative eigenvalues. So you will have lambda 1 plus of h, lambda 2 plus of h. So the positive eigenvalues. So here is 0. Etc. So you have an increasing sequence tending to plus infinity of positive eigenvalues, and you have also a decreasing sequence of negative eigenvalues. So that I write minus lambda 1 minus of h. So lambda 1 minus here is a positive number. So and then you have all the others, lambda 2 minus of h, etc. to minus infinity. And I will not maybe have time to explain this, but 0 does not belong to the spectrum of this operator. It can be proved. So 0 does not belong to the spectrum. And so the spectrum of this Dirac operator can be written like that. So the spectrum of DHA is just the union of these positive and negative eigenvalues, okay, as I wrote on the picture. So I'm sorry. So lambda 1 plus like that. So so the aim of this talk is to describe these eigenvalues, lambda 1 plus, lambda 1 minus, etc., when h goes to 0, so in the semi-classical limit. But first, I need to make a comment about a symmetry of this operator, so called the charge conjugation. So what is this? So the charge conjugation is an operator C, say the following operator. So sigma 1 phi bar. So from C2 to C2. Phi bar just means that you take the complex conjugate of both components of your spinor, and we have the following. That the domain is stable by C. So like that. So this is the domain of, the domain of DHA. And maybe you have already noticed that the domain does not depend on the vector potential. So if you want, you can also write this domain as a domain of the operator with minus A, like that. DH minus A does not depend on A. And the reason for which you want to put a minus here is that if you compute C DHAC, you get minus DH minus A, just by computation. And from this equality, you deduce that the spectrum of the operator with vector potential A is related to the spectrum of the operator with vector potential minus A. So the spectrum of DHA is the opposite of the spectrum of DH minus A. When A equals 0, when A is 0, you see that the spectrum is symmetric. is symmetric with respect to 0. In general, it's not the case. The spectrum is not symmetric with respect to 0. And we will see that in the theorem I'm going to state, especially in the semi-classical limit. We will see that there are very different behaviors from the positive and negative eigenvalues. Yes? No, there is no question.
No, that seems.
So, okay, let's talk about the results, the semi-classical results. So, results. So, the aim is to describe the spectrum when h goes to 0. So maybe I have to say that the limit h goes to 0 is the same as the strong magnetic field limit. It's the same. And to state my my results, I will make the following assumption. So this is an assumption for the whole talk, that the magnetic field is positive. So the magnetic field is positive on omega, like that. And I will use the following notation for the minimum of B. So B0, the minimum of B on omega. And I will also need the minimum of B restricted to the boundary. So the minimum of B on the boundary, like that. So I will use these notations. So there are two results in this talk. So the first result is about the positive eigenvalues. So positive eigenvalues. Like that. So to describe the behavior of the positive eigenvalues when h goes to 0, one needs to some kind of function called phi. So consider the following function that we already saw actually in the talk by Michael Thunquist. So consider phi this smooth function on omega, so real valued, such that so the Laplacian of phi is b in omega, and phi being 0 on the boundary. So I recall that I assume that b is positive, so that phi is subharmonic. In particular, phi attain its minimum, phi min. It is attained in omega and not on the boundary. And phi is negative on omega by the maximum principle. So this phi will be convenient to describe the results and also actually to generate a vector potential associated with the magnetic field. So as vector potential, we take A being the perpendicular gradient of phi. It's an immediate verification that the curl of A is the Laplacian of phi, and this is B. Okay, we can choose this vector potential, this special vector potential, because because omega is simply connected. Okay, so now I need an assumption to state my result about the positive eigenvalues. So assumption. Now, this assumption is on phi. So first, phi has a unique minimum in omega, a unique minimum. unique minimum at some point. So x min, like that, so in omega. And this minimum is non-degenerate. So the Hessian of phi, so the second derivative at x min, is positive. So these are my two assumptions. And maybe some of you have have a natural question. Okay, can you give examples when such an assumption is satisfied? And yes, you have a natural framework when this assumption is satisfied. So when, for example, when b is constant, b equals b0, so a positive number, of course, and when omega is strictly convex, and omega strictly convex. We can check that these assumptions are satisfied. So it is related to results, to old results by Cavol. So before stating the result, I need to introduce some functional spaces of holomorphic functions. So the first functional space I need to introduce is the Segal-Bardman space. Segal-Bardman space. So what is this? So it is denoted by B2 of C. This is a subspace of entire functions. So U's belonging to so entire functions, and such that some weighted L2 norm is finite. So such that something called NB of U is finite, and NB of U is the following integral. So over R2 of U y1 plus I y2 squared times the exponential of minus the Hessian at x min of phi y y, so dy, like that. So when this norm is finite, okay, this is called Segal-Bardman space, and it's related to the function phi, which has a non-degenerate minimum at x min. And the second functional space I will need is the RD space, the usual RD space. So so H2 of omega. So this is made of holomorphic functions on omega, and such that the restriction of U to the boundary exists and belongs to L2. So I will denote that like this. The norm, the L2 norm on the boundary of U exists and is finite. So the RD space. Corresponding to this, so this will be called NH of U here, the RD norm of U. And so corresponding to this norm, NH and NB, I will use the distances, so distance B and distance for the RD norm, distance H, like that. So now here comes the theorem concerning the positive eigenvalues. So theorem. So theorem plus, if you want. So this theorem states one-term asymptotics of the case positive eigenvalue. So consider K. Consider K. And so we have lambda K plus of H. So when H goes to 0, you have the following. So there is a huge constant here. So here you have distance for the RD norm between z minus z min. So z min is essentially x min written as a complex number, so to the power k minus 1. So the distance between this polynomial, this very special holomorphic function, and some subspace of the RD space called H2K of omega. I will give you the definition in 1 minute. So divided by the Bargmann distance between z to the power k minus 1 and some subspace of polynomials of degree less than k minus 2. So this constant is squared and times something exponentially small, e to 2 phi min divided by h. And here you see that you have also a power of h in the one-term asymptotics, and that when k becomes large, you see that this is a very negative power of h. So what are these quantities? So where so H2K of omega is a subspace of the RD space such that the derivatives of this function u up to the order k minus 1 vanishes at z min. So for all k between 0 and k minus 1, like that. And pk minus 2, so p minus 1 is the 0 vector space, and pk minus 2 is just the space spanned by 1, z, etc., z to the power k minus 2, like that. So this is the theorem about the positive eigenvalues when h goes to 0. In particular, if you look at this, you see, for instance, that all the first eigenvalues, when h goes to 0, become simple eigenvalues due to the presence of this power of h here. So maybe I have a remark here. That this result shares common features with a result that we obtained in a previous paper about the Dirichlet-Pauli operator. The Dirichlet-Pauli operator. So Pauli operator. So this operator is essentially the following. So P is sigma dot P minus A squared. So, and it can be written as LH plus, LH minus. And so in a previous paper with the same co-authors, we performed the spectral analysis when h goes to 0 of this operator with Dirichlet boundary conditions on omega. Dirichlet boundary conditions. And essentially, we perform the spectral analysis of this one, LH minus. And LH minus, what is it? So LH plus minus is the magnetic Laplacian, this one, plus or minus H times B. And so we studied in this previous work the case with the minus. And under the same assumptions as for the theorem plus I have just stated. And what we were able to prove for this operator L minus is that we have essentially the same kind of asymptotics for the case eigenvalue. I say essentially because in the Dirichlet-Pauli case, we have just upper and lower bound of the case eigenvalue, and we are not quite sure that the upper and lower bound that we get match in general. And what is surprising here is that we get exactly the same exponential decay when h goes to 0 for the Dirichlet-Pauli operator, so the formal square of the Dirac operator, and here for lambda k plus, this is the case eigenvalue of the Dirac operator, and we get the same kind of exponential decay with the same phi min, with the same 2 here divided by h. And maybe yes, I have also to say that I recall you that phi min is negative, so this is really exponentially small. So this is the first result about positive eigenvalues, and I'm going to state the second result about the negative eigenvalues. So what about them? So first, we have a rough result. So let's call this theorem minus. So this theorem gives you the asymptotics of the first negative eigenvalue. So there exists a universal constant. So a universal constant. So called A0 between 0 and square root of 2, such that lambda 1 minus, so I will call you lambda 1 minus is positive. And it behaves like that, h to 1/2 times the minimum between square root of 2b0, so b0 is the minimum of b, and a0 times square root of b0 prime, the minimum of b at the boundary, so plus small o of h to 1/2. So this is for the first eigenvalue. So probably your natural question is, okay, what is this universal constant A0? So what is it? What is A0? So A0 is related to the spectrum of the Dirac operator. So A0 so is related to the spectrum of some Dirac operator of the magnetic Dirac operator with constant magnetic field, with magnetic field equals 1, equal to 1, on the half space, on R2 plus, to the half space. So if you denote by dr2 plus, the corresponding operator, with constant magnetic field with the so-called MIT back condition, then the spectrum of this operator can be written like that, as the union of minus infinity minus A0 and of 0 plus infinity. So this A0, this positive number, is the spectral gap of this simple Dirac operator on R2 plus. And so we have a second result. Ah, there are some children somewhere. So the negative eigenvalues are strongly connected to the shape, strongly related to the shape of omega. So let me explain that when B is constant. So assume that B is constant, that B equals 1, say, and that the boundary is an analytic curve then you have the following theorem. So theorem, say minus second version, an accurate version, if you want. So consider K larger than 1. Then lambda K minus of H can be written as, so sorry, I have to say something first. So there exists a universal constant, say a constant called C naught, positive, such that lambda K minus of H behaves like that. So H to 1/2 A0. So it is in accordance with the result for the first negative eigenvalue when B equals 1, plus H to 3/2 times C naught times the nth eigenvalue of some operator called Q effective of H, so plus small o of H to 3/2. And so what is Q effective of H? So where? So Q effective of H is an operator on the boundary of omega defined as follows: ds plus some.
Excuse me.
Yes.
In the formula, it's lambda K.
Yeah, it's K. Yes, it's K. Of course. Yes, it's K. Because on my notes it's N. And this effective operator is a second order operator, ds plus th. So th is a number depending on h, minus the curvature of the boundary squared divided by 12. And th, what is this? So th is just the volume of omega divided by h times the length of the boundary of omega minus a0 over square root of h plus pi over the length of the boundary. And ds is the standard notation for minus I ds, where s is the curvilinear abscissa. So the curvilinear coordinate on the boundary, curvilinear coordinate on the omega. So what can I say about this? So this C naught. So this C naught is also related So this is a remark. Is also related to this operator that I called DR2 plus. And especially it is related to the dispersion curves associated with this operator. So and to its dispersion curves. So obtained after a Fourier transform with respect to the tangential coordinate. Obtained after a Fourier transform.
Sorry, Nicolas, for interrupting.
Yes.
What is K? Is it K? Again, K squared over 12?
Kappa is kappa
okay.
squared is the curvature.
Ah, so okay.
And so this T naught is related to these dispersion curves, and that's something that we did in our work to describe. So maybe I will just say that. So we described these dispersion curves. These dispersion curves. I will not say much more about this because it was a work in itself in the paper to be able to have some description depending on the Fourier parameter of this of the eigenvalues of our family of 1D Dirac operators. How much time do I have?
3 minutes, but even more if you want.
Three minutes off.
But let's say 5 even.
Or maybe even less actually.
Even less, yeah.
Maybe what could I say? What could I say? Oh yes, I can make a final comment. So this theorem plus and minus are so their proofs rely on on a characterization of the eigenvalues of our Dirac operator. Of the eigenvalues of our Dirac operator. And this characterization is some kind of nonlinear min-max principle. Inspired by a min-max principle that we found in a paper by Doldo, for instance, by Dolbo, Esteban, and Seri. But we adapted this nonlinear min-max principle to our framework. For the positive eigenvalues, we strongly use this nonlinear min-max principle, and for the negative eigenvalues, it's somehow another story. We perform a microlocal dimensional reduction to the boundary. Reduction to the boundary. That's how we get an effective operator, but by macrolocal techniques. So the famous, some people call that the Grushin method. And that's how we get some this. That's somehow how we get this effective operator, and and this constant C naught related to the Fourier transform of our Dirac operator with constant magnetic field on the half plane R2 plus, and probably I will stop here.
Okay. For the talk. So, are there questions or comments? Do you have a couple? So, Etienne, please.
Yes, I have a question. So you were talking about the relation in one of your remarks about the relation with the Dirichlet-Pauli operator.
Yes.
Right. And so the reason why the Dirichlet-Pauli is not the square of this one is because of the boundary condition.
Yes, exactly.
Okay, so then you can deduce that everything comes from the boundary, right? For these eigenvalues, or what?
Yes, if you change the boundary condition, you will get something completely different a priori. But actually, our strategy can be used also to deal with a family of boundary conditions of the same kind as the infinite vast boundary condition. You have actually, this is a special case in a family of boundary conditions, and it works exactly the same. But says that the case of the Dirichlet-Pauli operator, it's somehow a degenerate situation in this family of boundary conditions. It's sometimes called, it's related to what is called the zigzag operator. The Dirichlet-Pauli operator is related to the zigzag operator.
I also have a question.
Yeah, sorry, may I just build a second on a question by Etienne? So it's very vague, so maybe you just say it's a stupid thing and then that's okay. But is there any sort of low energy or non-relativistic relation between Pauli and Dirac? So is that the reason why there is this analogy between the eigenvalues, or can I think of that analogy being generated by this sort of connection?
So I'm not sure to understand your question, actually.
Yeah, okay, no, in fact, that's too vague, probably. That's why. No, I'm just saying, so in a way, Pauli is the low energy, say, limit, well, in a very vague
yes.
way of Dirac, right?
Yes,
That's
yes.
what I'm thinking of. So there is a connection. So is this probably the reason why you find similar behavior? So I'm saying the limit you're considering can be thought of as a non-relativistic limit.
Actually, yes. Let's go back to to this comment. Actually, what I didn't say is that for Dirichlet-Pauli we have essentially something like that.
Yes.
But for Dirichlet-Pauli, this RD space is not equipped with the same norm as for this this asymptotic expansion. It's not this. It's an RD space, but it's for Dirichlet-Pauli. In this RD space, you have also the function phi involved. So it looks the same, but the constants are not the same.
Okay, so
and so
it's not clear. Okay,
no, it's not clear.
Okay, so sorry, Pavel, please go.
No problem. So may I now?
Yes.
So your definition of C0 contains the squared curvature, which suggests that if the boundary is not smooth, if it has an angle, then you will have a different result. Any guess what to expect in that case?
I don't know. It's a very good question. I have no idea. We didn't consider, say, corners, but
well, that's usually the sign, because then if you make the bend of the boundary sharp and the curvature finally becomes delta, but then it comes the square delta, which is a singular interaction. So
But I think it's a very good problem to consider, say when omega is a corner, and even study the operator with constant magnetic field in a corner. I don't know if it has been done before.
So more questions?
I have a question.
Yes.
Besides
please.
your MIT boundary condition, would it be possible to consider any other kind of boundary condition?
We can consider other boundary conditions. As I said, in some family of boundary conditions, this MIT back condition is a special case in a family of boundary conditions. But if we if you want, we can also consider a family of boundary conditions going from the so-called zigzag operator to the infinite mass boundary condition. There is a continuum of boundary conditions for which our analysis applies as well. But away from such specific conditions, I don't know.
Okay. And in your case, in the two-dimensional case,
yes,
your phi has two components. Well, you have two components, right?
Yes.
Yeah. So is it reasonable to consider four components in two-dimensional case?
Yes, I would say it's reasonable, yes, at least from the mathematical point of view.
So you mean physically not very reasonable?
Physically, I don't know, but there are some models where when you have four components, yes.
Okay.
At least in dimension 3, I am sure.
Okay.
Any more questions? Okay, I do have just curiosity. So, do you know anything about the eigenfunctions? So, for instance, in particular, in the negative case, I think they are supported close to the boundaries.
Yes. So, for the positive eigenvalues, the eigenfunctions are essentially localized, say, near this x min, essentially. So, in some rough sense, they are close to x min. And for the negative eigenvalues, say that so you have the eigenfunctions have two components. So so says that the upper spinor is localized near the boundaries. This for sure we have from our analysis, but for the other one it's not completely clear.
So maybe even supported inside the other one. That sounds strange. No, well, no. Yeah, it's right, because you have two
components, and the eigenvalues are exponentially small, and somehow there is a relation. So actually our analysis through our nonlinear min-max principle somehow reduces to a problem with only one component. And there is a relation between the first component and the second component.
Yeah,
and the second component is obtained essentially by taking a Cauchy-Riemann derivative of the first spinor, the first